like that Aditya-L1 okay, sorry. So you said like that Aditya-L1 will be sending like the data in the TBs, I mean in the terabytes. Uh,
not able to record that.
so
The maximum disk which is there is
yes. So actually that I actually want to ask, like can't we develop any kind of a real time syncing mechanism for that? Because it is generating in the data in the terabytes, and we are just receiving the data in the like 100 GB of data. So there can be a kind of a data loss in between. Yeah.
very far.
Yeah.
So any satellite, there are different orbits. One is the sun synchronous polar orbit, but then that is looking at one position in the Earth for certain duration.
Yes.
If you have a number of ground stations, no problem. But that means every ground station you have to pay. Like your mobile phone, how many companies you can take? Oh, अच्छा, level with that. हाँ, नहीं मेरा तो कमाई की तो वो ऐड हो ही जाता है. So, geosynchronous concept itself is like that you have a continuous telemetry, and that will allow you to download terabytes of data, and that's what happens for solar dynamic observatory. Geosynchronous orbits are typically 50,000-60,000 kilometer, and the near Earth orbits are much closer, 700 to 800 kilometer. So these are then you have better telemetry. Even if you have say half an hour of visibility every 2-3 hours, it depends on how many times it will rotate. You can download a lot of data, provided you have such antennas and things like that. You have certain bands. But we wanted to go to Lagrange at one point, because that's a very suitable point to look at the sun continuously. Because if you have a low Earth orbit, there is also eclipse season. You won't be able to, because of the inclination, certain seasons you will not have a visibility to the sun. So you will have, again, loss of data, loss of sun. So that is also not desirable for space weather and all that. So it's again a compromise between these things. We are now having, space missions going out of ecliptic plane. We are all talking about our own ecliptic plane. There, the visibility is solar orbiter sends data once in few months. But still, we want to go to different vantage point, because sun looks different. We are looking at the sun like this all the time. It's this way. We don't know what is happening in the pole. But I didn't mention too much. All your measurements of the polar fields and all that are erroneous because of the projection effects. So if I can go up and look at the pole first time, that's what solar orbiter is going to do. So instead, it cannot go to out of ecliptics. It's making a number of things and then going up. So, but the telemetry is very, very poor. Only few hours we observe. Rest of the time it's sleeping. But half an hour of new look is preferred than better than continuous old look. So it's a compromise between different things. Yeah.
But you go in also with lot of power to transmit the data as well. So
Yes, sir.
you have to take that.
Sir,
She started first. Yeah. Go ahead.
With respect to sunspot and the magnetic field, you mentioned about the Stokes parameter. So can you tell more about it and how it has been?
Yeah, so you need actually a spectropolarimetry separate class for that. It's just not about sunspot alone. So the spectral lines have certain properties, right? Because of different transitions and so on and so forth. And the polarization is giving you information about the plane of vibration of these particular elements, and what all different, depending on the direction of the propagation and the inclination of the magnetic field, what all effects you will have in the different Stokes parameters. So I don't think it is half a minute answer possible. So spectro, you have not had anything in the spectrometer or spectrograph or any course on atomic spectroscopy?
Spectroscopy course,
Yeah.
Zeeman splitting, and then in the presence of magnetic field, you have this. Not only Zeeman splitting happens, the light also gets polarized, right? That you must have learned. So essentially, that is what we are going to measure. So it depends where light is going to be polarized, circular polarization or linear polarization. Depends on whether the magnetic field is parallel in the linear direction, so parallel to the field or perpendicular. So that will dictate whether you get the circular or linear polarization. So all these polarizations are spaced into 4 parameters. One is Stokes IQ, UV. The V parameter mostly deals about the circular polarization. Q and U deals about the linear polarization, and I is the total intensity. So those are the parameters which we need to actually measure both components of the magnetic field. So you get the vector magnet. That is in a nutshell, but there is lot
Yeah,
of
you have to reconstruct also, because you need to also worry about the atmosphere through which this is coming through. So that's why the polarization can change because of the intervening atmosphere. So there is an inversion which is required. So you need a theoretical model which will allow you to then talk about how much intensity is there, which is directly linked with the field strength, the orientation. As I said, it's a combination of the linear and the circular polarization, which will dictate all the 4 Stokes parameters. It's just not for sunspot, any magnetic field, even in the laboratory, the same thing.
Okay, so I have a very general question regarding the long-term solar variability. Actually, I have been through some research studies that publish long-term variabilities affecting the Earth's global temperature and all. So I just want to know whether is there any research works currently going on that is like more into the Earth's overall stability, or especially in magnetic field kind of orientations related to Earth?
Yeah, there are a few things I would point out. See, we are far away from the sun, thankfully, at an appropriate distance away. So Earth's magnetic field is generated because of internal properties, not because of the sun. We are much away from that. So in terms of its, of course, Earth is a part of the solar system. If sun becomes a red giant, we will be affected. But in its current state of affairs and next million years, we are expected to be, sun is expected to be in the main sequence and so on. Its overall radiation output, which we call the total solar irradiance, is considered to be constant, but which is not a constant. It does vary 0.01% with the solar cycle. If that variation is more than 0.01, it will certainly affect our climate, because see, that's the reason the modern minimum period, probably there was something wrong in the total solar output. Now, having said that, now it also appears that it's not only the total solar irradiance, but the spectral irradiance. Means, if you measure the luminosity in certain wavelength pass bands, then it appears that the variations are more. The 0.01% what I'm talking about is total. But the UV particularly, if that variation is much more, it may have much more impact in our atmospheric layers. Ozone and other atmospheric chemistry can change. And that will affect, so there will be a definite effect on the thermal properties, because the thermal property is just not by internal thing of this of the Earth. It's essentially radiation, what it is coming, and our atmosphere. Our atmosphere has also grown with the Sun-Earth system development, right? We had our atmosphere, and people are talking about, of course, Earth has its own magnetic field. That's why we are also there for habitability. Somebody was talking about and all that. The magnetic field of the planet is very, very important. So again, to answer your question, the thermal properties will have a effect, or the atmospheric. So we call it space climate. That subject is area different. Definitely, there are people who work on it. There are a number of nature papers on that. So Sami Solanki, the Max Planck group, where we also collaborate with, but we have not ventured into that field yet, because the data what you needs much longer duration. Just 100 years से कुछ नहीं होता है. उसमें आपको at least several thousands, if not millennia, So people use cosmogenetic, other sources, I-score, treating. So there are other, data sources which people use, and they work on it. So it's a pretty well established field. But don't go by small data sources. हमारा वही season change हो रहा है, cloud हो रहा है, ये सबसे ज़्यादा कुछ नहीं होने वाला है. Because there are people who believe that हमारा यहाँ पे cloud formations and all that also has a. Of course, there will be some effect, but it's not. It's more of a causal than really physical.
Sir, actually, in solar cycle. Can you?
You want to see the solar cycle?
Yeah.
Okay. Yeah, I will show you any solar cycle.
Yes. Anyway. Actually, we plotted filament solar cycle plot also. With comparing to that, it matched. But another thing, if we see the time taken from minima to maximum is suddenly peaked, then but when the maxima to minima again drops, it takes too long, like slanting. Why it is happened?
Yeah. So what he's talking about, just for the benefit of this thing. So when you say filament, what are you plotting? Filament numbers, filament area. What are you plotting?
Filament count and area.
Yeah. Okay. So see, filament number and filament area both will have certain linkages with the magnetic field availability. So what he's talking about, I didn't again get into that. See, this is called the rise and this is called the decay. So there are often relationship between how fast the solar cycle is rising and how slow it is decaying. So you already see that there is often the slower decay rate, and there are physical reasons and all that. We have theory for that as well. Now the question is, the filaments are not always representing the active regions. Filaments are also related with the quiet region, quiet sun. So it is not a best proxy for that way or comparable with the sunspot number, because sunspot number is only representing active regions, whereas filament is not. So on the decay phase, since this is a much slow rate, you have much more quiet sun contribution there. So it is not comparable. It's not the same. You're not comparing apple with apple. You're comparing apple with oranges. So that's the reason.
And final question is, when the solar during the solar cycle, when the magnetic disturbance is reduced, the solar cycle be in minima stage. When it is higher the magnetic disturbances, the cycle become maximum. Then when I compared with the SVS data, magnetic disturbance with solar cycles, I noted that in the equinox months, the magnetic disturbances are higher. Then solstice months, their magnetic disturbances are lower. Why is it happen on that?
Yeah, there are many different things you're talking about. Again, that's a problem. So when you say magnetic disturbance, what are you meaning? Is it the CME numbers you're looking at, or are you looking at DST index?
CME number.
CME number. So, and then you said something to with Earth's magnetic field. So they're different. Okay, they're different thing. So of course, the CME number has a direct linkages with active region number also. Having said that, again, CMEs have different classes also. There are slow CMEs, there are fast CMEs. Now the question is, are all the slow CMEs coming from active region? No. So slow CMEs are often coming from other regions also, prominences particularly, and filaments and so on. So there are a huge amount of work which you should talk to Vaibhav. And he has done for last 2-3 cycles, and we have looked at all this. So you have to again segregate the data appropriately before you compare. When you say just CME number, it doesn't make any sense. You have to say CMEs, fast CMEs. Then the fast CMEs are very much correlated with the sunspot number. When sun is more active, you have fast CMEs. When the sun is quiet time, you don't get big CMEs at all. You only get the slow CME. So you have to segregate the slow CME. So you have to compare slow CME with certain things, with fast CMEs with certain things. So that is what is very important. Unless you do that, you will not be able to compare things. Again, DST index is the Earth's magnetic field orientation is also very important. These CMEs carries a magnetic field which also has its orientation. That orientation is crucially dependent on the Earth's magnetic field orientation. If it is not aligned, then it is not making any impact at all. So those things also has to be looked at. You have to find out the apple and apple again to compare. Okay.
Yeah, thank you, sir.
Terabyte of data is generated by AstroSat. So
AstroSat.
sorry.
AstroSat doesn't generate terabytes of data.
Sorry. Yeah, from Aditya. So like, which one do
No,
you
we are
select
not
to-
going to generate terabytes of data. This is what is it's a futile exercise now. How will you generate terabytes of data? Because you don't have storage.
Okay.
You have given a 50 gigabyte
what
camera. You're going on taking movies. Kaise hoga?
नहीं हो पाएगा. How do you
So the
select-
hard disk which is there on board is 256 GB.
Okay, so you we are bringing back whole of that data.
Yeah. So otherwise, so there are a lot of programming is required.
Hmm.
What data will be downloaded first
Yeah, that was the
in
question.
patches and all that. So there are a lot of planning required on this.
Okay.
You submit a proposal which will generate a terabyte data, it goes to bid.
We
So
can
there is
take-
a time allocation committee who will look at, whether the proposal which you have submitted is feasible. So you have to be given a tool which we plan to develop, which will tell you how much data will be also generated by doing this observing program.
We take only one or two more questions because after that.
Yeah, these questions actually can come after my Aditya presentation. I mean, I will
Okay,
make that.
yeah, just to add one, what is a turbulent diffusivity, if you explain in some similar term?
It's a transport coefficient. So, like conductivity you have different transport coefficients when you do a fluid mechanics. Then this is another parameter which is dictating how in a turbulent medium, how efficient the turbulence is.
Okay, and I will add as a supplementary question, when will you observe the next solar cycle based on the observation? Like, is it in, and how it will like impact the Earth? Like
We
the
are
when-
observing
like-
all the time solar cycle. Maxima, you mean
yeah,
to say.
exactly, yeah, magnetic, like when the maximum will be the high.
So again, we expect it is next year. But again, as you see here, which one is the peak? Can you say this? So they're all reproduce the yearly average thing, and there you see it's almost few years where the maxima is, and there is a double peak here. It went up, then went down, and again went up. We have explained all this theoretically also. So really, it is hard to say 2024 December 15 will be the maxima. So it's going to be a spread over a certain time. We are on the ascending phase, that is guaranteed.
We should
Yeah.
now continue with the Aditya-L1 presentation, I'm sure, which you all are looking forward to. So let's have that presentation, and after that we can have questions.
I could locate my presentation. This is a long-term intro. Okay. Okay. So Aditya-L1 is India's first space observatory. We also call it the observatory class mission, because you can have small payloads and fly with other, other partners and all that into space. But this is a dedicated space observatory, like AstroSat, but AstroSat was in low Earth orbit. AstroSat doesn't generate that much of data. Of course, because the other objects which AstroSat looks at needs several minutes of exposure. So the data volume is much too less. This is, I think, a sort of really path-breaking mission from India. Make in India project, Atmanirbhar Bharat, whatever you call it. I think this classifies or this satisfied all those conditions as well. I'm a tiny fellow representing the science working group. the chair of the science working group. I'm the co-chair. Shankar will be here hopefully by Sunday. He's also the project scientist. He's the main scientist for the Aditya mission now. I have been involved with the few payloads, primarily the coronagraph and the suit payload for few decades now almost. When I returned in India after a year or two, there were discussions what we should have, where we should go and all that. So at that time, there was only a coronagraph with one imaging instrument was supposed to fly at the low Earth orbit. But then with time, we became fatter and we also demanded much more. And it is again, thanks to ISRO. ISRO came back, rather ISRO chairman, and I think I dedicate most of my lectures to Professor U.R. Rao, who was a former ISRO chairman. Then he became he was a cosmic ray physicist actually. He studied from Harvard, came back, was there briefly in TIFR, then ISRO took him over. Very fundamental scientist, but then, space mission, and then of course, space mission was involved with mostly defense and remote sensing and all that. Science was not the priority for any space program, in India at least. So this remarkable change was possible because of, again, Professor U.R. Rao. He just called some of us in his office and suddenly called and said, would you like to go to Lagrangian 1 point? It's like, would you like to go to attend a meeting tomorrow in the US, something like that. I said, what is this guy talking about? It's bad. Because I was aware of, Lagrangian 1 mission because I've been involved with SOHO for the last 2 decades. I know what it deals with. And SOHO has changed solar physics, he said, we want more challenging missions. Low Earth orbit, अभी इंडिया के लिए कुछ भी नहीं है, जहाँ कहीं जाना है जो और कोई नहीं गया है. Of course, he's referring to our neighbors. So I said, yeah, of course, it will be fantastic. But then if we are going there, it's not worth to take a small payload and go there. So we should have the opportunity to have many things more. So obviously, announcement was given, but that is something in India we still have not grown with. And 1 month time or 2 months time was given to submit proposals and all. So hurry-burry, we put up proposals from different places. And eventually, we have 7 payloads on board. There are many institutions who are involved. Of course, some are involved with hardware development, some are involved with science. And we hope that number will grow. The idea of all these, exercise, even these workshops, is to, enlarge the user community for Aditya. And we hope some of you will be, interested in this and join. Some institutions are from anywhere to use Aditya data. Of course, first question will be when it is going to be launched, when the data will be available and all that. So I would defer those answers to Shankar, who is coming. I know somewhat a bit of it. It is expected to go August, but there are lots of questions. Everything has to go the right direction to happen that. All the payloads have been delivered. They have undergone the vibrations also. It's not a very, very pleasant exercise. All these sophisticated instruments are shaken like this to see whether they break, because that is inevitably they are going to exercise. So it appears that they have all passed, but now the integration happens at different part of the spacecraft. So that's the state we are. And as you see here, many logos are there, and there are several hundreds of people from science, from engineering are involved. If I include all the engineers, probably it will go into thousands. So I'm not naming anybody. But I would also like to share this slide with you, because some of us are involved with creating vision document for India for next 20 years. And this is a plot we generated. See, this is, this area, what you see here is operational. And multi-wavelength, the aspect which I was talking about. Of course, these are radio, GMRT, UT ready telescope, go with the Nur. Then we have visible the 3.6 meter dot, which you will see the 2 meter Himalayan Chandra telescope from Ladakh, the Mount Abu telescope. Then we had our first, space mission in multi-wavelength optical UV and X-rays, AstroSat. And of course, these are high energy gamma ray experiments, which is happening. ठीक है, डिस्कनेक्ट हो गया था. वापस आ गया. Okay. So if I now go to the right panel, you see the space is completely filled. So there are so many space missions which are planned. Of course, Aditya-L1. So this is 20 to 2040 onwards, I was saying. So this is a 20-year vision which we have now projected. These two are expected to launch within next few months. XPOSAT is a polarization measurement. This is a thing led by RRI. And these are all, proposed, I would say, not accepted. In optical region, we are projecting NLSC. The land is already procured. The funding is awaited. This is a 2 meter class telescope, which I referred to. There is a proposal for a 10 meter class optical and infrared telescope from Himalayas, from our Ladakh site, from IA. And these are the, primary X-ray missions. Of course, upgraded UGMRT is already producing fantastic results, as you know. And again, they have expanded, programs as well. Now, what is other thing which I would also highlight is India is partner to the 30 meter telescope project, 10% partner. Of course, it has some issues in terms of its site at Hawaii. We are partnering Square Kilometer Array and LIGO India. These are all approved projects. So the future is pretty bright. And then also there is a space gamma ray mission projected with Indian stuff. You also hear, I was told that there is a Japanese mission for Sun, which India is going to provide the launcher. There is also likelihood that the Americans are interested to go to Moon again, to land in Moon, but India is going to provide the launcher. So this is something which has happened last week after PM's visit. He did not mention, I think, explicitly this one, but he did mention about going to the space station. Indians are going to go to the space station. So the good thing about, I would say, our credibility is improving. Because I think when we were young, we didn't have good credibility. And when we went abroad, they wanted to work everything with their sort of, style and so on. But now with our indigenous mission, I think they are getting better confidence. Still, we have to go a long way. And these are our test missions, I would say, to improve our credibility in the international scenario. So, as I indicated, there are 7 payloads. The main payload is a coronagraph, which is going to sit in the top deck, which will have 3 visible and 1 infrared channel. And for the first time through the infrared channel, as I indicated earlier also, we are going to measure or try to measure the magnetic field in the corona. This has been a dark energy problem of solar physics. We have not been able to consistently measure magnetic field. There have been sporadic, measurements or inferences from other indirect ways of seismology and so on, get an estimate about the magnetic field, but systematically, consistently, we do not have. So this will be the first attempt of its kind, which is led by IIA. I will talk more about it. Then there is a near UV full disk imager, which is going to operate between this 200 to 400 nanometer, and which will look at, sun as a, it will be able to resolve all the features on the surface, but also it can, in principle, integrate and get the total solar irradiance as well. But you will be also having possibilities of getting the illumination from, say, active region versus quiet sun and so on. So segregation wise also you can be you can do that. So a lot of reconstructions will be required. This is led by Ayuka. Then, so these two are remote sensing instruments. So we call it remote sensing when we are going to Lagrangian at one point. We are remotely looking at the sun, and we are only measuring the emission which is coming from there. And these are called in situ measurements because the particles which are going to come from the sun because of certain activities on the sun will be in situ measured at Lagrangian one point. So there is one instrument called aspect, which will primarily allow us to get a better solar wind distribution in terms of charge, mass, and orientations, and so on. There is also a low energy plasma analyzer package led by SPL from BSSC called PAPA. And these two are Solex and Helios. These two are X-ray instrument, but they're going to, these are X-ray spectrometers. Again, another two remote sensing instruments, but they are going to look sun as a star. So we do not have X-ray imaging capabilities from this. So that's a limitation. But again, it has a very good spectral and temporal resolution. So it will allow us to do spectroscopy, the changes in the atmosphere, particularly related with the flares. And as you know, there are different kinds of flares which is there in the sun, small flares, big flares, and so on. So that's why there are two different instruments, because one particular detector cannot actually detect the small fellows and the big guys in terms of energies. So that's why one instrument is called Solex, which will look at smaller flares. And the Helios will primarily look at acceleration of the particles and so on, related with the very dynamic events. This is again done with your Rao Center and PRL. Then finally, we have a magnetometer also to measure the magnitude and nature of the interplanetary magnetic field. This is developed in LEOS. I think and Isaac, it's called UR Rao Center now, with the name of Professor Rao. That will give an estimate about the CMEs. If it comes, then if it is carrying certain magnetic cloud, then what is the properties of this magnetic cloud. These are all very important instruments for space weather things. So that's the overall locations of the different payloads. As I indicated, the biggest elephant on the top of the thing is VLC, the coronagraph, and then the suit instrument is going to sit next to it, which is the about 35 kgs. This is 185 kgs, I was told. Eventually has become, and all other guys are much smaller, hanging on different locations, like a monkey on the different side of the payload. Of course, after the deployed view, the solar panels will look something like this. Oh, this is again an old slide. Last year, I think I gave the same presentation, so I've not changed this. Now, we are going to go to Lagrangian one point. It will take about 3 months plus to reach there. The way we will go is this is Earth-centered orbit. It's like, if you want to throw a stone, you do this, karte phek diya, and then this will have a cruise phase. And then this is very crucial to get into Lagrangian orbit. See, Lagrangian one point is a stable point. There are 5 Lagrangian points for a two-body system. If you put a third particle, then essentially those are stable locations. Once you are there, you do not need too much of fuel to maintain this orbit. Of course, time to time the correction is necessary, but essentially the force between the sun and the satellite roughly balances the force between the satellite and Earth, at this big halo orbit around this. Yeah, so not strictly stable. That's why we need to orbit it around it. Yeah, but the 5 Lagrangian points, if you draw a 3D simulations, you will find as a locations where things are, long lasting, so to say. So these are the, again, list of the payloads, combination of 4 remote sensing and 3 in situ instruments. And the major objective, again, there could be hundreds of things that can be done from all these 7 payloads, but you have to, if you have to list out few, then of course understanding the coronal heating, because we have possibilities of spectroscopy in the corona, but we are going to look at the inner corona. I will talk about what is inner corona, the part of middle corona. There is a new definition of middle corona now. There's a review article you can refer to. And the solar wind acceleration, because the sun also continuously losing out some amount of mass. And yesterday you were seeing this, that the solar wind also has a asymmetric pattern. You have slow wind, which is coming primarily from the equatorial region, and the fast wind from the polar region. But then why the polar region is faster? So there is somewhere things get accelerated, and we still do not understand the acceleration very well, because even now we do not have very good quality inner corona graphic data. And very close to the sun, we are going to look at 1.05 to 3 solar radii, and that region, consistent spectroscopic observations are also not there. See, corona is only visible from the ground during the total solar eclipse. That happens rarely, and that happens only for a few minutes. So running big experiments is not possible. You cannot carry those big telescopes to those remote locations where the totality path is. So of course you have to depend on space platform, but space platform has lots of UV things on disk, but off limb SOHO had spectrographs, and SOHO spectrograph has provided some information, but it has not information in these wavelengths which we are talking about. We are going to look at several highly ionized iron line, which are probing plasma temperatures of 1 million K and higher. Majority of the EUV observations which have been from space is around 1 million K or less. There are not that many lines representing this. Only when there is a flare and things like that, then you see certain spectral lines in the EUV. So those have been the limitations from the so far space platform, and that's what we are going to fill in. Understanding the initiation of the coronal mass ejections, flares, and near-Earth space weather. So essentially what we are talking about is, since we are looking very close to the sun, there all this acceleration happens. Once it gets accelerated, of course, we have lots of coronagraph, and we do follow its kinematics and all that. But initially, where exactly it gets accelerated is not very well understood. There are lack of understanding on that because of unavailability of data. Same with the flares, what its impact because of the 2 X-ray spectrometers, which will allow us. Coupling and dynamics of the solar atmosphere, this will be primarily done with the SOOT instrument, because the SOOT instrument has many filter images, which is probing different layers of the atmosphere of the sun. So when you look at different layers, you know how one layer is talking to the other one. That's what the term coupling we call about. If there is a change in one particular layer, what is the response or effect of that particular dynamics into the another layer is can be studied from SOOT instrument as well. And then solar wind distribution, temperature, anisotropy, all these things will be done from the particle payloads as well. So yeah. So helio orbit, this is the very big orbit depicted here. This is elliptical, but not perfect ellipse, as you see from the drawing as well. So that is to maintain the sort of distance from the L1 and continuous look to the sun as well. So as he said, we are not going very close to the L1 point. We are making a big halo orbit around the L1 point, and that halo orbit takes a very, very long, I don't remember the duration, the distance to the several 100,000 kilometer around that point. Yeah. They're not symmetric also, you can see this. So that's why they're called. Okay, so the importance of the inner corona, you see, as I was mentioning, we had C1 coronagraph on Soho, but unfortunately that died after 2 years. It had again a Fabry-Pérot, as I indicated, it's a risky instrument. So beyond 98, we did not get any data from C1. C2 is still operational. It's more than 2 cycles now. So was launched in 1995. Still it is operational. Also, the fact is that C2 coronagraph is so good, C2 and C3 coronagraph is so good. This is C3. No, C3 picture is not here. This is a ground-based coronagraph with a low spatial resolution. Our thing is very similar to this, but again, ground-based means, you have to be weather dependent. And we cannot, and there are a lot of scattered light from different sources and so on. These coronagraphs are sitting in high altitude mountain. There is also snow and all that, which also affects heavily the observation. This is best, the perfect occulter you can have. So coronagraph is nothing but a occulter, like, you put an artificial disk to block the solar light, and then you see this. But the point is that this disk, if you put, there are lots of scattered light from the side. And sometimes that light is much, much stronger. Not sometimes, it's more, all the time, it is much stronger than the signal which is from the corona. But this occulter is sitting much away from us. It is an external occulter, moon. So that is a perfect, because all the scattered light probably doesn't reach us, right? So that's why we get a perfect, view of the corona, but very rare. And only snapshots, that much of detailed thing is not possible here. So that way, even 40 years of space coronagraphy, the lower corona remains practically unobserved, especially in the visible and infrared wavelengths. Because as I said, space people normally are looking at UV and other wavelengths, but optical and infrared is not too much monitored from space. So Aditya mission with the coronagraph, we will be focusing on this. We have a much higher, sort of a larger coronagraph. This was a 5 centimeter, coronagraph, or 5 centimeter telescope. We have a 20 centimeter diameter, almost 20 centimeter primary mirror. So that, of course, collects a lot more photons. We'll have and higher cadence data, because all these are taking of the order of several minutes. And here the problem is we have too much of cadence. It's the other way around. Now we are scratching our head how to observe, because it takes with the exposure time of 5 milliseconds. So and these days, the cameras are also much more efficient, so it doesn't need that many photons. So that's our challenge. But depending on the modes of observation and all that, we should be able to observe it at a very high cadence for observing very dynamic things. It changes every, say, half a minute or so, or even faster. So that's the field of view which is projected on the coronagraph taken from eclipse. We hope we'll be able to, I do not know, that we really will be able to get such a picture, but that's a hope. But the other beauty is that we have this spectrograph channel, which is going to look at very close to the sun and with multi-slit also. So typically a spectrograph has a single slit which disperses the light and produces the spectrum, right? But when you take a single slit, you only have information about only these pixels, right? So the way we do a 2D map is we just scan this, the pointing is changed, and then you create, this is called raster scan, and you produce a 2D map. But to produce a 2D map, depending on the exposure and how fast you can rotate the mirror and so on, it takes about a half an hour. But we want to have it faster, like half an hour mein the dynamics change ho jata hai. So if you have multi-slit, then it will be reduced by that many slits, whatever you have produced. So here we are using it for the first time from space, again, 4 slits, and we'll be able to produce a spectral image at 3 different wavelengths. I will briefly talk about those, and they're all 3 ionized state of iron. This is a close-up of that. So you can imagine that if you have, these are called, yesterday somebody was asking what is helmet streamer. These are equatorial region. There are active regions here. You have polar regions where, field is more open. You have polar plumes, they call it. So many different structures have different kind of dynamics. There, time scales of changes, temperature, magnetic field, they're all different. So we'll have possibility of, looking at all these different regions, throughout its lifetime, at different, moment and so on. Then the CME observation, so far what is happening is, since we have this LASCO C2 coronagraph, which is looking at that CME, and we have the full disk imager, but in between we do not have any data. This is a missing region. Periodically, I mean, occasionally you have a ground-based observation and all that, but not always. So this is the missing location, and when a CME comes up, so we will fill up our region like this. So our white light channel will cover up to this field of view, and the spectral channel will cover this gap. So we are not only only have imaging, we'll have spectral information. See, modern day astronomy can be only done if you have, see, frankly speaking, imaging gives you beautiful images, but do not allow you to do all the physics. If you want to do the physics, you need spectrograph. You need to get the temperature, you need to get the density, you need to get the velocity. So all these physical parameters of the emitting plasma is only possible for astronomy if you have spectroscopy. So a combination of imaging and spectroscopy makes the entire thing much richer, much more valuable in terms of the physics. So that's why I think this is very, very unique, because other coronagraphs do not have any even the spectral capabilities. So for the first time, we will have a spectral capability which is perfectly filling the gap, which is not there from space. So that's why our thing is very important. Exposure, I said, 200 to 5,000. I mean, we can just, because exposure possibility is there even all the way up to 5 milliseconds. But if we go for 5 milliseconds, you can imagine how much data it is going to generate. So we have to figure it out how, what, level we can store the data and all that. So typically we will operate in this kind of mode. 1 minute kind of cadence we will probably be able to generate. Every minute we'll have this information. So here you see again, this is a white light, this is a ground-based coronagraph. Occasionally you have this thing, and you see here how nicely these features are connected. These ejecta connected, and we hope that we will be able to generate this. So it may contribute to imaging, UV white light counterpulse. And so what also happens is that sometimes you have UV images which will also probe a plasma, but which has a different temperature. So probably it is not the same plasma which UV is seeing as compared to the white light, because white light is essentially the scattered electrons from that enhanced region what is there in the space in the corona. They themselves are not actually emitting. It is a reflected light, reflected photons or electrons from the disk, which is making that place bright, and that's what we image in the white light. On the top of that, in the inner corona, we are going to have emission lines, which is directly coming from the plasma region itself. So there are lots of things which can be done. There is we see that the CME, here you see the CME, all the parts of the CME is not moving with the same velocity. I guess you'll have CME lectures in detail. There are 3-part structure of a CME. The core is, here you see, then there is a flux rope, and then there's a void in between, and so on. So, so we'll be able to track the CME all the way from inside to all the way outside. Of course, other coronagraphs are there, and the core material is essentially related to the prominence, which is cooler and so on. Whether it is really cool or not also has to be probed. So since we are going the first time going to have a spectrograph, we'll be able to measure the temperature and all that also there. So there are quite a few things which we'll be able to do. So here, this is a typical CME velocity profile is shown as a dotted line. Because of the lack of data cadence, since we have one image and other image is separated, this is how you see it. Of course, these data points were from C1. Unfortunately, this C1 did not operate for a very long period of time, as I indicated. Only 2 years it operated out of all these 22 years of operation. So here, this is all data missing now currently. So we hope that we will be able to provide this. And as you can see, this is the flare profile. So flare also has a pre-flare stage, then there is a rise phase, and then the decay phase. Again, the decay phase is always much longer. Of course, the different physics is involved in the decay phase and the rise phase and so on. So that if you could relate with the CME velocity profile, then you see CME has an initial phase, then this is an impulsive acceleration phase, and then the velocity becomes more or less uniform. And with this uniform velocity, it moves. So this is a typical example of a fast CME, because it's 1,000 kilometers. So these are fast CMEs related with major flares, and that's why this is the X-ray flux which is plotted here. So these kind of studies will be much better, doable with our, instruments. Of course, we will need other coronagraph as well. This is again, I will highlight that don't be understanding that although this is a space observatory, we have 7 payloads, that's not enough. Probably we'll need another 20 odd payloads from other places. And that's how we do solar physics today. And that demands a much larger data volume and the machines to help us to do this job. Future is, is machine learning only. So, and as you can see here as well, the cadence makes this thing. We don't have data unless it is continuous. You're always, interpolating and so on. And this is the current understanding, but I think we need to do much better. This is also another point that these images, this is from C1, the initial phases. Again, few data only available from C1. Here, the pixel resolution is about 5.6 arc second per pixel. And we're going to do 100% better than that. So it's 2.7 arc second per pixel now with our instrument. This is again an example shown from eclipse images. What is showed here is images taken with 2 different filters. So this is one line, RN11 7892, which is depicted by red color here. And then, RN14, which is 5303, which is indicated by green filter here. So if I superpose these 2 images, they always do not really co-align. So that means corona is very much multi-thermal, and it's not that the same plasma is obviously emitting in the 2 temperature. There is some overlap, but there are quite a bit of difference as well. This is 2006, 2008, 2009, 2010. The corona looks very different, right? So again, you see very clear example of solar cycle. The extended corona is crucially dictated by the global field structure. It's just not the active region alone. It's a global magnetic field where here you see that during the minima period, you have more, sort of, open fields and not so bright and all that. But here you see, everywhere. Structures are there everywhere because, of course, these structures are rooted with some active region somewhere. Here you don't find that many active regions during the minima period and so on. So, it is important to monitor the corona continuously. Just one observation, one eclipse per year is not going to be enough. And for the eclipse only, we had some spectroscopic measurements, which is not there from the space yet. So we have enormous potential with the coronagraph instrument. This is the global field. These are some work which is done at CESI. There is no student from either Kolkata, but Dipankar and his group is working. In fact, I'm a faculty in either Kolkata CESI also. That's why you find 3 affiliation for me in my opening slide. So there was a Center for Space Sciences opened with the multiple faculties at different institutions. Shankar is also a faculty in CESI, and Dibyendu leads that at IISER Kolkata. They do this kind of predictive models. Just before the eclipse, he produced this image. Before the eclipse day, he published it one day before, put it in archive. And these are the magnetic field lines and so on. And it appeared that the next day things did match reasonably well. So now we have reached a stage where we will do numerical models of magnetic field based on, of course, certain other inputs on the surface magnetic field measurements from other data, not from our data. But then if we are able to reproduce the coronal field map from VLC or from our own coronagraph, that will be fantastic, because that gives a real validation. Because during the eclipse, we are not measuring field. What we are actually seeing is this structure. We assume that this structure is governed by the magnetic field lines, because wherever you have magnetic field, you have material there confined. It's all MHD in that assumption. But we don't know what is the reality. There will be variations. And so for the first time, there is a possibility of having these global MHD predictions and compare our observations. And if you go on comparing day to day, probably both will be improving. It's just not one off, right? So there is a huge potential for improving the models or improving our inversion also, because our inversion also is dependent on certain assumptions of the magnetic field measurements. So this is a enormous new area. Nobody has done much work. There's one paper, Abjelator, some 10 years back on this thing. But the observation was from a ground-based facility, and hardly people believe in that. So I hope that this will bring in some new avenue. Shankar is the main person for understanding that magnetic field. He's not going to talk about it that day. He's going to talk about the Solex instrument, because he's the PI of that instrument also. But you can discuss with them. So that's the Dibyendu's work. So the background is the eclipse image, and this is the magnetic field configuration which he showed. So it doesn't look like it's too bad. He could manage to get all the closed field regions, all the open field regions. And as you can see, if you have this global field, then you will have a direct model for solar wind also. Because the solar wind structure, where it is slow and fast, is crucially dependent on where field is closed and where field is open. So this is a direct. So we need to inject this field on global solar wind models as well. So there are lots of collaborations, lots of machines to work together required. This is the SUIT instrument prelude. So what is happening is from space, this is the profile. I think Krishna showed this. If you look at temperature profile of the sun, we have temperature minima, and then there is almost 1,000 kilometers, again 1,500 kilometer odd, up to transition region, the temperature suddenly jumps, and then you have the coronal temperature. So we have a lot of EUV measurements from space, primarily from SDO, earlier also from SOHO. But this region is not so well regularly observed from space. As you can see here, this is H alpha, mostly observed from ground. And then, this is oxygen 5. No, this is UV, not oxygen 5. This is UV continuum of 1600 angstrom here. And then this magnetic field measurement and visible. So this area is something which SUIT is going to focus on. And so that's the area we'll have. So if I look at this also curve you saw yesterday, if I assume a black body, sun is a black body, and if you see the total flux coming from the sun, this is typically peaking at the optical. But of course, there are absorption lines and all that, what here also you see, which Krishna also mentioned. We are going to look at only this. So this flux looks like is much lower than optical, but you see the variation in this flux. So the challenge for any detector to measure a weak flux and the high flux is enormous. So this is also another reason why such, cameras were not built, or challenges are much more. The contrast has to be much, I mean, you have to basically be able to 3 orders of magnitude flux difference be able to measure. Because you give it exposure, you have a possibility that either it is underexposed or overexposed. So that means you have to have a detector which has a very big dynamic range. That's what we call it. It should be able to, measure small fluxes. That means it has to have a very big potential well. So all these things, I mean, the camera which is there in the coronagraph will be rubbish for this instrument. Cannot do anything because it has a CMOS. It has only a few tens of thousands of potential well. Here you need at least, 100,000s of, capacity potential well to be able to detect few photons to, some 70,000 photons as well. So that's the sort of, challenge. This has the suit instrument has only one detector, but it will have a filter wheel. So you rotate the filter wheel and one image you can take in one. So that again, it is not simultaneous measurement in all these different filters. But if you like to just take an observation with one filter for a very long period of time, you can do it. See, the ILMT, if you go and see there, I mean, all astronomy, they take images in UV, RI and all this, have also the same challenges because we don't have that many cameras. We have only one camera, and then, but of course, the coronagraph is exceptional. We have several cameras, 4 cameras on board. Simultaneously, we are measuring in the 4 thing. So that's a luxury which normally people do not have, and that really, really allows you to really look at simultaneously the response. See, 1 million K plasma gets heated up, and then within few seconds you get a 2 million K plasma responding that you can see. So the dynamical studies can be studied much better if you have multiple cameras, which unfortunately we do not have here. But what you can do is it covers different layers, photosphere, and then we have actually going to focus on 2 different spectral line, primarily on magnesium. This has been observed very recently only from one of the small satellite program called IRIS, again a NASA small satellite program, and that is showing us a lot of new features. It's a very bright line, magnesium. It has a bit of complicacy also in its interpretation, but we have understood the line a little better now. And since this is a much broader line, you are going to observe at the line center and the wings and so on. When you are looking at a spectral line which is broad, if you are looking at the line core, then you get information about, say, higher heights. When you are looking at the wings, you are looking at the lower atmosphere. So by looking at different locations on the of the spectral line with a small little narrow window, you will be able to